Hello. All right. Hello, everyone.
Hello.
It's my privilege to be with all of you, and a warm welcome to day 2 of reInvent 2018. Over 7 years ago, when we started building Aurora, we had a simple mission. We wanted any person, anywhere in the world, to be able to run and access databases. And all they would need is business application. They would not need to worry about provisioning, need highly skilled operators managing their databases, make trade-offs between performance, availability, durability, and cost. And by doing so, we believe we can transform everyone in the world to reimagine the databases in the cloud. Hi, my name is Kamal Gupta. I am a senior engineering manager at AWS. Today, I'm going to show you not only the new innovations we did in Aurora, but also how we did it. And we're going to talk about how we are adding new capabilities like Multimaster, Peril Quarry, serverless into our Aurora offering. Let's dive deep into Aurora MySQL. Our vision for Amazon Relational Database Services is to give you choices and recommendations so that you can make the best decision for your applications. On the one hand, we offer open source solutions for our customers who likes the simplicity and the cost effectiveness of them. But the challenge is that they lack enterprise-grade performance and reliability that our customer needs for mission-critical applications. On the other hand, we also offer old guard commercial-grade database engines for our customers who need enterprise-grade performance and reliability, even though they are expensive with lock-ins and punitive licensing terms. One of the early feedback we received from you guys is to build something that combines the best of both worlds. And we have created an Aurora for you. With Aurora, you no longer have to make the trade-offs. You get the commercial-grade performance, availability, durability, at the cost and simplicity of open source solutions. And it's delivered to you as a managed service. Here are some of our customers who have been using Aurora: NASDAQ, Hulu, Airbnb, Zynga, Ancestry, some big names. As you can see, Aurora continues to be the fastest growing service in the AWS history. With that intro, I'm going to first talk about performance, and then we will deep dive into availability, durability, and manageability. You know, when databases first came out, they looked like this: monolithic stack in a single box. And with local storage, we were trading availability and durability to get better performance. Over time, we decoupled compute from storage. And this allowed us to be able to scale, customize, and manage each of those layers separately. But the monolithic stack still remained the same. And then we added more such boxes. It's the same SQL stack everywhere. Nothing changed. Moreover, now we need heavyweight distributed consensus protocols like Paxos or Raft for data replication. but they perform poorly for databases because of multiple phases and multiple rounds and different synchronization points involved. And they add jitter and latencies to your queries. With Aurora, we made two key contributions. First, we pushed down log applicator down to the storage. And that allowed us to construct pages from the logs themselves. This is really cool because we don't have to write full pages anymore. Unlike traditional database engines, where they have to write both logs and pages, Aurora only write logs. And this means that we have significantly less I/O, and we have to do much less work on the engine. We don't have any checkpointing anymore. You don't have to worry about cache evictions or background flushing anymore. Second, instead of using heavyweight consensus protocols, we use 4 out of 6 quorum with local tracking. And the reason we can avoid these heavyweight consensus is because we can exploit the monotonically increasing lock sequence number from the database engine to order the writes. And so when storage node receive the writes, they just accept the writes. There is no voting involved and back and forth to whether to accept it or not to accept it. And we'll see both of these things in a bit more detail later. But what you get out of these, you get significantly better write performance. You get read scale out because the replicas are sharing the storage with the master. You get AZ+1 failure tolerance. So Aurora stores 6 copies, 2 copies per AZ. Even when you're managing your large fleet, even your data centers, the nodes constantly go up and down. That happens. But we argue that while that is happening, an entire AZ goes down on top, Aurora can handle it, no problem. You get instant database redo recovery because we don't have to do anything. All we have to do is find out a point and do some math before the time of the crash. Let's look into each of these things. So again, no more trade-offs between performance, availability, and durability. Let's see how the first optimization, the log applicator, works in action. Here we have 4 transactions with master and replica, with storage at the bottom, 6 ways replicated. Let's say transaction T1 started. And as you can see, all the 6 storage nodes and replica received that change. And so if master and replica have to read that page again, they will get the latest version of the page. Okay. Now let's say T2, T3, and T4, all of them started. Notice that the changes in purple are coalesced, but the changes in blue and green are kept on the side. And this is because replica clock is still at purple. And when master and replica reads, they will get the correct version of the page. For master, as you can see, the storage node applies the blue and the green changes on demand on the fly. And eventually, the replica clock will go to green, and we will coalesce and garbage collect the delta log records. So hopefully you can see how we can construct pages from the logs themselves. Now, why does this matter to you, right? Let's take a look. Here we ran a sysbench workload to compare the I/O profile for stock MySQL running on EBS with Aurora. On the left, with MySQL running on EBS, you can see it has to replicate all kinds of data. And as a result, it has to do 7.7x more I/O than Aurora. And results in 35 times less transactions. The other thing to note here is that step 1, 3, and 4 are synchronous. And so what that means is it adds jitter to your application. And we will see that in a second why that matters. In the contrast, Aurora uses 4 out of 6 quorum. So it's much more resilient to tail latencies. So even if one of the storage nodes is taking time, that's totally okay, because we just need 4 acknowledgements. Again, here we ran the sysbench read and write workload on both MySQL and Aurora. And as you can see, Aurora did 10 times better on the write workload and 2.5 times better on the read workload. Here is another example with bulk loading and indexing. Again, Aurora is 2.5 times faster than MySQL. Let's take a look at the read replicas for your OLTP reads and OLAP queries. On the left, we have MySQL bin log replication, typically used in the MySQL community. And on the right, we have Aurora physical replication. Unlike MySQL, where it has to transmit the full rows and statements for the bin log replication, Aurora only transfers the log records, which are just the delta changes. The other thing to note is that the bin log has to apply all the writes on each of the slaves. With Aurora, there is no write I/O on the replicas. In fact, for the pages that are not in the buffer pool of replica, there is no read I/O involved for replication purposes. So to summarize, there is no write I/O, there is no read I/O for replication, and there is no extra storage involved. Here, we are comparing the Aurora logical replica lag with the Aurora physical replica lag. So the experiment that we ran here is in the same instance. It's the same hardware, same software, just switching from bin log replication to Aurora replication. So it's apples to apples. As you can see on the left, the graph is in seconds. Within first 10 minutes of heavy load, the lag went up to 5 minutes. With Aurora on the right, consistently stayed under 20 milliseconds for hours and hours.
Do you mind explaining what's logical and physical? Because both of them say Aurora.
Yes, so logical is the bin log replication, and physical is the log record-based replication. I'll take the questions in the end. Let's take a look at the second optimization. Again, the same setup with 4 transactions, storage at the bottom, 6 ways replicated. We also have a durability tracker on the right and set of waiting transactions who have not been acknowledged back to the client yet. Let's say we started all of those transactions, and at some point, the state looks like this. And as you can see, the orange changes from transaction T1 already achieved 4 out of 6 quorum. So we can mark that committed and acknowledge it back to the client. Let's say at some later point, state may look like this. As you can see, the changes in blue corresponding to transaction 3, even though they achieved the right quorum, we have not acknowledged it yet. To understand this better, let me step back a bit. Let's see how flushing works in traditional databases. In traditional databases, you accumulate the set of log records, put it into a log buffer, and group commit. You get the second set of changes, and you commit it again. So it's all sequential. And as soon as it's flushed, you acknowledge back to the client. With Aurora, instead, when we receive the write, we immediately issue it to the storage node. And so it may happen the write issued later may get flushed first. It's going to different storage nodes. But instead, we take care on the return path, that we make sure that we only acknowledge in the order. It's important, otherwise we will have holes in the write-ahead log, and that will not work. And the reason it matters to you is because the flush operation is a heavy operation. You don't want the sequential writes there. It adds latencies and jitter, and we'll see that in a second. Now let's say at some other state, let me try this. The state may look like this. And as you can see, all the changes achieved the quorum, 4 out of 6 right quorum. And so we can acknowledge all of them. And finally, everybody in the storage node gets all the changes. So there is no consensus. There's no waiting anywhere other than just doing a 4 out of 6 quorum. And the reason is because we exploited the sequencing from the head node, from the database node. I didn't talk about reads here, but if you're interested, please refer to Aurora's SIGMOD paper. We have a paper on that. Or you can catch me after the call, after the talk. Here, we ran sysbench again and recorded the latencies. As you can see, Aurora not only has the lower latencies, but also is much steadier. More precisely, based upon the standard deviation of the 2 data sets, Aurora is more than 200 times consistent and has 25 times lower latencies. This is despite the fact that in this example, we are pushing 45 times more work than MySQL. So you may be wondering, what is this big spikes that is happening? Well, this is MySQL checkpointing. And when MySQL has to checkpoint, it has to do a lot of background writes, which interferes with the foreground transactions. And so to summarize, we get significantly better latencies and less jitter because of 3 reasons. 1, we don't have checkpoints because we construct the pages from the logs. Second, we can do out-of-order flush. Third, we do not have any heavyweight consensus, and we use 4 out of 6 quorum. So even if 1 or 2 storage nodes is taking time, that's okay. What else we did? Here are some software improvements example that we did in last few years. On the left is the MySQL thread model. You get a connection, you open a thread. Clearly that doesn't scale with connections. Instead, with Aurora, we added a thread pool with event-based epoll and latch-free task queue. Allows us to scale much better with high number of connections. You know, when you're pushing so much load in the system, if you have a global lock, they will all contend. And all the other efforts that you did with respect to throughput will go in vain. With MySQL, any changes, any updates will lock the whole lock table. Instead, with Aurora, we allow concurrent access to the individual lock chains. So there is no contention. Not only software improved, but also hardware also improved. And as you can see, year over year, Aurora is getting better and better. Aurora can do 200,000 writes per second and whopping 700,000 reads per second. And it's getting better each day. Well, some of my customers comes to me and ask, what about parameters, performance parameters? Well, Aurora already pre-tunes or auto-tunes different parameters for you on different hardware configuration. Unless you're doing something peculiar, you should get the best performance out of the box. Now, there are few performance parameters like InnoDB log file size, InnoDB flush at transaction commit, sync bin log, that allows us in MySQL to get better performance. But that usually comes with a trade-off. Here is one example with InnoDB log file size, where you can get better performance, but you also increase your recovery time. The reason is that if you increase the log file size, you're effectively delaying your checkpoint. And so if you delay your checkpoint, the more redo logs you will accumulate. And when MySQL has to recover from the crash, it will have to apply all of those log records on a single thread. And that takes time. So again, no more trade-offs. Well, so much about single master. Let's talk about multi-master. Before we jump in, let's take a quick look at the space. When we first started, we had one node SQL, but it was very hard to scale. Over time, we did manual sharding, but it was hard to manage. You can get hot partitions. If you have to run DDL across these shards, it's very painful. Not to mention if you have to do cross-shard transactions, clearly not there. With NoSQL, we achieved the scalability and is offered as a service, but it fundamentally lacks the support for transactions. And so the customers that I talk to, they love the transaction model. They love to be able to model about it, to be able to reason about it. It's very hard to write apps with eventual consistent systems. With Aurora Single Master, we addressed most of them but there were few gaps. And with Aurora Multimaster, we're addressing most of those gaps by adding write scalability and database write availability for our customers. Let's take a look at some of the existing multi-master solutions. First, we have a shared disk model with caches fused together. The challenge here is that they use pessimistic locking. The other big challenge is that they require high cache coherence traffic. And so you either need expensive interconnect between the nodes, typically put together in a small data center in a room, or you suffer from hot blocks ping-ponging across the nodes. Then there are systems which use read-write set technique. Basically, the idea here is that if you want to modify anything, you first read something and then modify based upon that value. And at the time of the commit, you check if anyone else has modified anything that you read. If someone did, then you abort your transaction. If didn't, you commit your transaction. And if you can do that for all the transactions in a particular order, you will always come up with the same outcome. And so what these systems do, they replicate the transaction and independently run them in the same particular order. And you get your distributed databases. But again, the challenge is that coming up with this particular order for all the nodes becomes a bottleneck. And finally, then there are systems, NoSQL-like systems, where data is range partitioned. They typically use Paxos within a partition and then 2 PC across the partitions. The challenge here is that if you have a skew in your access pattern, which is quite typical, then you will end up with hot partitions. For example, let's say you partition by date time for your queries. You will end up writing to at the end of the partition. Also, they happen to use heavyweight consensus protocol for commits. With Aurora, there is no pessimistic locking. There is no global ordering. There is no global commit coordination. Instead, Aurora Multimaster is based upon three techniques. Number one, optimistic conflict resolution. To understand this better, let's say we have transaction T1 and T2. If they write to two different tables, there is no conflict, and they can independently write. But if transaction T1 and T2 modify the same page, P2 in this diagram, one of them will achieve the quorum, the other one will not. So one of them will win, the other one will retry. One thing I forgot to mention is that with single master, we used monotonically increasing lock sequence number from the head node. With multi-master, instead of having a single monotonically increasing lock sequence number, we have partitioned monotonic LSN sequencing from the head node. And we use that to order the writes. Second, we have a decoupled system. With logging layer pushed down to the storage, there is no coupling between the transaction layer and the physical layer, the logging layer. And so we can manage the physical conflicts in the storage and the logical conflicts between in the database layer. And by logical conflicts, I mean the transaction conflicts. And we will see in a bit with a better example what that means. Also note that the storage volume is divided into set of partitions, and there's no coupling involved. They don't talk to each other. And there is no coupling between the head node itself. Finally, we use microservices architecture to run services in the cluster so that if any one of them is temporarily down, it doesn't impact your whole cluster. These are minimal, independent, and resilient services. In short, Aurora only coordinates when it has to coordinate. Let's see that with examples. Let's say we have clients C1 and C2 talking to Blue Master and Orange Master respectively. Let's consider a simple case where they are writing to different tables. They both begin the transaction. They update different tables. And they both commit. No synchronization. Now the same setup, but more interesting case. Let's say they write to the same row of the same table. Again, they both start transaction. BT1, which is the blue transaction, OT1, which is the orange transaction. And they write to the same row of the same table. In this case, the Blue Master get the 4 votes, so it will acknowledge back to the client. And the Orange Master will ask the client to retry. Now, just because there is no physical conflict doesn't mean that there is no transaction conflict. Let's see that with an example. Again, the same setup, and they're both trying to write to the same entry of the same table. They both started at transactions. And let's say C1 updates the table 1 with row 1 and page 1. And at some point, let's say this change will replicate to the Orange Master because there is a asynchronous replication going on. Again, there is no synchronous coordination involved. It's an asynchronous replication that happens over time. So let's say in this example, C2 is just waiting, and it will issue the update eventually. Now, note that if C2 have to issue the update at this point, it will act on top of the latest version of the page. And so from storage perspective, this is okay. The storage, if you want to write your next version of the page, sure, there is no conflict. Because you're updating the latest version of the page. However, we detect that in the database itself. And the way we detect is we use MVCC. And so the idea is you look at the transaction identifier in the row who modified it, and you see that, okay, this transaction, this row seems to be modified with transaction ID, let's say 10, but this doesn't seem to be committed yet. And once you find it out, you say, okay, let me roll back. It's not allowed. And eventually, C1 commits. So as you can see that there is no global lock manager here. Here we ran, again, the suspense workload. And you can see we first started with one node and added another node at 5-minute mark. and another 2 nodes at 10-minute mark. At 15, we simulated by crashing one of the nodes. And you can see it came back up at 16, and lives move on. This is really cool. Okay, this is about writes, right? But what about reads? How do we do reads in Multimaster? More precisely, how do we achieve linearizability? To illustrate the problem first, let me go through an example. Let's say John and Bob are very good friends. And one day, John decided to propose to Sarah. And so he updated his status and sent a post. If John simply do a local read, we'll see, Bob, if simply do a local read, we'll see, okay, John tried, looks like it didn't work out. However, if he would do global read, he will find out that Sarah accepted. So he can pick up the phone and call John to congratulate him. So the basic idea is you get to read your own local changes, but if you want to read the global changes, everything that happened in the whole cluster at that time, you need global reads. And that is linearizability. Let's see how we do it. In this example, we have 3 nodes, node N1, N2, and N3. Client issues a request to N1. N1, in turn, sends a hello request to N2 and N3. And when N2 and N3 receive this request, they respond with a timestamp at which they saw this hello request. Let's call the time T2 and T3. N1 then waits to get the changes from N2 and N3 till time T2 and T3 respectively. And once N1 gets all the changes, it performs the read to the storage and return the results back to the client. So you can see it adds latencies only if you're doing the global reads, and it's configurable per session. Now, there are other solutions out there who does this on the write path, but the challenge is that with the write path, you don't have an option. If you're doing it on the write path, you have to always do it, because you fundamentally have to introduce a wait to make sure the time has advanced, so that if once I return the acknowledgement, anybody else will start the transaction, will always see the time afterwards. So you have to wait till that point in your write path. And you have to do that for every transaction. Instead, if you do it in the read path, you can choose. You may want to pay the penalty, you may not want to. So in summary, we achieve linear scaling with optimistic conflict resolution, continuous availability with microservices architecture, enterprise-grade durability with 6 copies, 2 copies per AZ. We also do backups on top. And we support indexing, constraints, triggers, procedures, functions for your relational database. Okay, so much about OLTP. Let's talk about OLAP queries. First is batch scans. And so the idea here is whenever you get so this is for in-memory workloads. And so let's imagine you have a big machine with a huge buffer pool. And if you are issuing a big query that has to scan a lot of rows, what happens is When MySQL receives a request, it asks the underlying engine, which is the InnoDB, to fetch the tuple one by one. And every time it has to traverse the whole tree, take the latches along the way, read the tuple, and process that tuple. And that is very inefficient. What we do instead, we get in batches. So we request to give a batch, and we tune that dynamically based upon the instance size and everything for you. On top, we also add just-in-time optimization to make it even better. Second is hash joins. I mean, the idea is very simple. You take the smaller side, build a hash table, and then you scan the outer side and probe into the hash table. But of course, in practice, it's much more involved. You have to deal with skews, you have to deal with duplicates. In nutshell, you have to minimize the number of passes you are making over your data set. Not to mention, you have to build an optimizer to decide when to use hash join, when not to. This optimization is relevant for eqjoin and works for both in-memory and out-of-cache workloads. AKP, in short, asynchronous key prefetch, is for non-eqjoins, or for some eqjoins as well. If, for example, you have smaller outer and you have a high cardinality index on the inner, that then it may make sense. But the idea is when you scan the outer, instead of looking up for each row inner and load the page from the storage synchronously, you prefetch. You basically look ahead the set of the rows and ask the storage to fetch those pages into the buffer pool. And so when the other thread comes and tries to look up, it will always find the pages in memory. So this optimization only works for out-of-cache workloads because that's what it does. It brings the pages in advance in the buffer pool. So as a result, we saw, on average, on half of the queries, more than 2x speed up with a peak speed up of 18x. This is a TPCH-like workload. The other big thing we did in this area is Peril Quarry. We GA'd that thing last few months ago. And so the idea here is to push the processing down to the storage. And this is very similar to what we did for logging. So we pushed down the log applicator, and now we are pushing down the query processing layer to thousands of storage nodes. And moving the computation down closer to the data means you will get much less data back from the storage node. And also it will reduce the buffer pool pollution, and we will see that in a second, why that matters. But before that, let me talk briefly about how we did it. On the left, with the gray arrow, the request comes in. We augment the request with the list of pages and the page LSN, or the version at which it is on. And we send it down to the storage. All the storage node involved in this query return two streams, clean stream and dirty stream. Clean stream is a set of records that has not been modified since the query started. The dirty stream is a set of records that have been modified since the query started. So for the clean stream, you can push that directly to the aggregator, right? Because there are multiple storage nodes here. All of them have to combine the results, right, before you can send it back. But for dirty stream, we first have to apply the undo, and then the SQL function on top, and then we feed in back to the aggregator. You combine all these streams from different storage nodes to get the final result. Now this is one of the problems. There are several other problems, like how do you get the list of pages in a way that doesn't affect your OLTP performance? How do you do flow control between the head node and storage nodes? How do you run these queries in a secure container on the storage? Remember, storage is a multi-tenant storage. How do you deal with failures in the storage node so that if one storage node goes down, your queries are not impacted? So if you're interested in learning more about this, we have a chalk talk on Thursday, or you can catch me after the talk. Now this is an active area of work. Today we push down predicates, projections, SQL functions, joins. For joins, we use semi-join reduction. Basically, effectively, the idea is to build a Bloom filter on the outer and send it down to the storage. And so storage node can filter it out. And you can see that, before that, so we ran again, the TPCH-like workload. And this is the result, by the way, just for PQ alone. And so we saw 120x time speed up, peak speed up. And 8 out of 22 queries saw an order of magnitude better performance. So because I was mentioning about the filtering, so on the left, you can see I ran a TPCH-like query 6, which is effectively a filter on the line item table. And you can see if you don't use parallel query, you will have to get 956 GB of data back from the storage node to head node and to process it in the database engine. But if you use parallel query, you can filter down that to 4 GB. And that's the only amount of data you actually get back. So that's 240x reduction in the amount of data that is being sent back from the storage node to the head node. And this is meaningful for you guys because this means it doesn't affect your OLTP performance. And on the right, you can see I use the data set 150 GB just to be easy on myself because the buffer pool size is right around there. The actual impact may be slightly more or less depending upon your workload. But the idea that I'm trying to reflect here is that as you're pushing your OLAP queries on top of OLTP queries, you can see that it will create a buffer pool pollution once you issue the OLAP queries. And it will bring in the pages that are not hot set for OLTP, and which will impact the OLTP performance. Okay, let's talk about availability and durability. So first, why do we need it? Why do we need AZ+1 failure tolerance? As I said before, when you have a large fleet, it's natural to have nodes go up and down. But that doesn't mean that AZ cannot go down when these nodes are down. It can happen together. So how does Aurora handle it? We keep 6 copies, 2 copies per AZ. So even if, let's say, an AZ goes down, you will lose 2 copies. An additional node goes down, you will lose a 3rd copy. But since you write to 4 places at the first place, you still have 1 copy left somewhere. Because when we did 4 out of 6 write quorum. You can also see if we would have done 2 out of 3 quorum, that will not work. Let's say we did 2 out of 3 quorum, 1 copy in each AZ. And let's say an AZ goes down plus an extra node goes down, so you lost 2 copies. But you did 2 out of 3 quorum, so maybe the 2 copies are right on these 2 nodes. And you have fundamentally lost data. On top, we do continuous backup to S3. Just briefly how it works is, again, storage volume is divided into partitions. Each partition has 6 segments. Each segment is 10 GB, or in fact, the partition is 10 GB, and there are 6 segments in that. And so what we do is we take the snapshot of these segments and any log records that have been written as of this time. And we stream that to S3. At the time of the restore, we first restore this snapshot of each segment and then apply the delta log records after that to get the latest version of the page, all the pages. And since this is done in storage, it doesn't affect your database performance. It's all happening in the background on different nodes. Now, there are times where we accidentally deleted a wrong table or forgot to put a where clause in a delete statement. So we have a database backtrack. Now, you may ask, why not just restore it, point-in-time restore? Well, this is much faster operation. You're talking about a couple of minutes versus a couple of hours. And so the way it works is, in this example, you can see we went till T2, and we realized, oops, we made a mistake. So we went back to T1. So we marked that window invisible. And then let's say we went till T4 in purple and realized, oh, damn it, we made another mistake. So we rolled back to T3. And so we marked that band as well, invisible. Now, one thing to note here is that these ranges or invisible markers are not destructive. It's not like once you marked it, you lost it forever. It's like a slider. So you can, yeah, exactly. You can go back and forth. So you can say, okay, oh, damn it, I went too far back. So you can come back, that's fine. We talked about this, so we get instant crash redo recovery. Basically, there is no checkpointing in Aurora, right? With traditional databases, you have to replay all the logs since the last checkpoint and apply that in a single thread. But with Aurora, there is no checkpoints. I mean, it's all happening in the storage. You just find out the point at which you accepted the last write before the crash. You can have up to 15 read replicas. You can define the failover order on them. Maybe you wanted only certain replicas in the same AZ. You want to keep your master in the same AZ. You can do that by defining the order. Or maybe you want to keep your replicas, the master of the same instance type. So you can define the order, and that will be useful. So when the master node goes down, we will choose based upon the failover order which node to pick up or which instance to pick up as a candidate for promotion. Now, replicas share the storage with the master. So anytime master goes down and replica takes over, even though there is an asynchronous replication going on, you still don't lose the data. The reason is it's the same storage. So only thing is, it may happen that the replica may be a little bit behind in memory. So the pages in cache may be a little bit behind, right? Because replica didn't know before the crash some of the things, let's say 10 milliseconds ago, what happened on the master. And so what we do when we promote replica, we figure it out what changed between the time master crashed and the time I was on before the promotion. And you find out the set of changes that happened during that time. And you just invalidate those pages and reread them from the storage back again, the latest version. Let's see how the continuous availability works with Multimaster with an example. Let's say there is an app with three nodes in the system. And let's say master 1 went down. Notice that the other nodes will keep on operating as before. And you can distribute your connections to the other nodes. And independently, while that is happening, the node that crashed comes back up. It's happening independently. And once it's back, you can add the connections back. Global replication. Now, the two reasons why our customers want global replication. One is the DR. What happens if a whole region goes down? And the other big reason is to be able to provide lower latency reads globally. So a good example would be like, let's say I'm building a travel booking website. Then the searches that is happening, people are doing all the time in different countries and regions. It will be served locally. And so that will be fast. But the actual booking may happen in a single region because only very limited searches results into booking. You can pay the cost at that time, that's fine. Just one example, may be useful. Let's talk about manageability. So this is again the feature we announced a few months ago. It's already in GA on 5.6. What this is, it allows you to have a single dashboard to monitor and root cause your load issues. And essentially, you can group by SQL, hosts, users, and weights over time, or over any of the metrics I said. So you can group SQL over weights, SQL over users, or users over hosts. You can do anything. Just check out the dashboard if it's better to just play with it. Now the problem could be you have a high CPU, you have a high I/O latency, or you have some lock weights going on. Once you look at this, once you identify the problem, you can take an action on that. You may want to tune your query or maybe add more resources, depending upon the situation. Again, this is done in a way that doesn't affect the database performance. We do not just simply use performance schema because that has an impact on the performance. We did several optimizations so that you guys don't see an impact to enable the performance insights. We simplified the management for you. You don't have to pre-provision the storage. It will automatically grow. You don't have to configure the number of replicas. You can just define the minimum and maximum, and based upon the load, we will grow it or shrink it. In fact, you can define custom endpoints, one for your OLTP reads and one for your OLAP queries. With serverless, we can scale the instance up and down. And so this is really useful if you have, let's say, a dev test workload or some sporadic workload, unpredictable workload. You can save a lot of cost. Even with the provisioned Aurora, which is the normal Aurora, we announced stop and start feature. So you can stop an instance if you're not using it. And it will be stopped for 7 days before it will automatically resume, or you can resume in between whenever you like. Now let's see how that works. To understand serverless, we need to first understand the 3 layers. The database proxy layer, where your application is connecting to. And notice that this is a multi-tenant distributed proxy layer. And so if any one of the machine goes down, it doesn't affect your whole application. Maybe there's a few connections going through that proxy. Second, we have a warm pool of Aurora instances of different sizes, all ready to go, so that we can scale you up and down quickly. And third, on my left is the monitoring service, which is basically continuously monitoring your database and seeing what's the activity going on. And if it see there's a spike, it will automatically grow. And if it see it's idle, it will automatically shrink it down. Now, the way you may be asking, how do you persist these connections? How do you make sure that there is no impact to the application? And so the way that works is you first attach the new instance as a replica to the old instance, and then you signal the original writer to find a point where there's no active transaction. I'm very loosely speaking here, but find a safe point, basically. And once you find out that point, since then, you respond to all the proxy with the message saying that, please redirect the traffic to the new instance and loop back anything that proxy is sending to you back to the proxy. All the incoming MySQL traffic back to the proxy. And once once the proxy gets this message, the control message, saying that, okay, you are asking me to redirect, that's okay, I got it, you're scaling. It will redirect, it will take all the MySQL incoming traffic from the node, from the database node, and redirect it back to the new node. And once it learns that, it will redirect, of course, the new incoming traffic directly to the new node and close the connection with the old node. And so you can see you didn't lose your connections. The connection persists while we are doing all this mumbo jumbo. Here is the simulation we ran, so you can see it for yourself. Finally, we are introduced a web service data API for your Lambda applications on top of serverless. And what this is basically you can send us an HTTP request and you no longer have to worry about connection pooling. We will take care for you. Here are some related talks if you're interested in learning more about Peril Quarry, serverless, and Multimaster. With that said, thank you everyone, and have a good rest of the conference.